Okay, so we've learned quite a bit about the theory. So we've said that because we are studying special relativity, our observables must be fields. Because we're studying quantum mechanics, our observables must be operators. So in a theory of quantum mechanics that's consistent with special relativity, our observables have to be operator-valued fields. So at each point in time and each instance in space, we have an operator, and that's our observable. But we don't really know what a quantum field is. We don't really have a good idea. What I'm going to try to do in this chapter is to actually construct an example of a quantum field. And the quantum field that we'll study is the free scalar field. So we're studying a free field because we think that's going to be the simplest. And when we say scalar here, this is referring to the Lorentz transformation properties of the field. Okay, so scalar means it doesn't change under a Lorentz transformation. And we're considering that again because we think that this is going to be the simplest situation that we could consider. Now, I'm going to write down some axioms that a free scalar field should obey. And every time I write down an axiom, you see if you agree or not. And I'm hoping that these axioms will make perfect physical sense to you, so that when we finally construct our field by solving these axioms, you'll understand exactly what we've done, and you'll have a good intuition for the quantum field that we have constructed. This method is not going to work, however, for interacting fields. And for interacting fields, we're not going to be able to write down some axioms and solve them. But I'm going to show you another method of quantizing called canonical quantization. Canonical quantization is a recipe. You're not going to get much intuition, but by using canonical quantization, we're going to reproduce the result for the free scalar field. The good news, however, is that canonical quantization will generalize, and we'll also be able to study interacting fields with canonical quantization. Okay, so let's get started with what I hope is a very well-motivated and easy to understand discussion of the free scalar field. So what is the free scalar field going to be? Well, I'm going to denote it as phi of x. And to specify this field, I want to write some equations that phi of x will obey. Well, the first equation that I'm going to write, let's call this axiom 1. I'm going to say that phi of x must commute with phi of y if these fields are space-like separated. And remember, that means if x minus y squared is less than 0. Okay? So I've written down a commutator equation. You're used to seeing commutator equations to define operators, so this shouldn't be a big shock. Now let's talk about what we've done here and why. Well, x here is actually x mu. It's a point in space-time, so it's some time and it's some position. Y is also a point in space-time. It's some different time and some different position. So if we calculate x minus y, well, this 4 vector is given by tx minus ty and x minus y. When we say x minus y squared, we mean x minus y mu and x minus y mu. So we are taking the contraction of a 4 vector with itself. Now, you know, if I contract two 4 vectors, this quantity is Lorentz invariant. And that's good. It means if one inertial observer thinks the two fields are space-like separated, all inertial observers will agree that they are space-like separated. So the axiom A1 is something that we are saying for all inertial observers. Now, what is x minus y squared equal to? Well, this is the square of the time component minus the square of the spatial component. This is negative for space-like separated. So that means the spatial separation is larger than the temporal separation. So if we were to use our old crutch of a space-time diagram, x. If we put x sitting over here, point x mu, and we draw in the light cone. So let me draw in the light cone now. There is the light cone of x mu. To get a point which is space-like separated from x mu, I need to pick a point where the spatial separation, so that's the spatial separation between the 2 points, is much greater, or is greater than, just has to be greater than, not much greater than, but it's greater than the temporal separation. But that means that y mu will lie outside of x mu's light cone. What does that mean? That means that, whatever I do at x, it cannot produce a disturbance at y. Now, one of the things I could do at x is measure the value of the field. It cannot disturb the value of the field at y. And from the last chapter, if we want the measurement of 2 observables not to disturb each other, we must ask that they commute. So this is why we require the first axiom. So this is really, we're putting in something about special relativity here by saying that when the operators are space-like separated, measuring the 2 of them should not disturb each other. Good. So that's the first axiom that we're going to write down. Please make sure that it makes perfect sense and you understand why we must require this of our field. What is the second axiom? Well, the second axiom is the fact that when we measure our field, so this will be the strength of the field, we want to get a real number, okay? So phi of x is going to be the size of the field at point x, and we want that to be a real number. Now, as usual in quantum mechanics, to make sure that our observable is a real number, we ask that our observable is Hermitian. So this should look like a very natural requirement to you. In quantum mechanics, whenever we have an observable, we ask that it's Hermitian. So P dagger was equal to P, X dagger was equal to X, H dagger was equal to H. And this was always for the same reason. It's so that the eigenvalues of the operator are real. With axiom A2, the eigenvalues of our field phi of x are going to be real, and the result of some measurement will be one of those eigenvalues. So we know we're going to get a real number when we perform this measurement. Good. Okay, the next axioms that we're going to study are all concerned with how our field will transform under transformations. And there's 2 kinds of transformations that we could consider. We could consider a translation, and we could also consider a Lorentz transformation, a rotation or a boost. So we're going to say how our field transforms under translations and then under Lorentz transformations, rotations and boosts. So that's what we're going to do next.